what the dot product kind of looked like, right? It was a multiplication of vectors. And it was very interesting because, if you multiply the magnitudes of the lengths, you kind of get an area of a rectangle because, or, some type of figure that looks like a rectangle. And that's kind of the precursor of what a cross product is going to be in a little bit. But first, we'll talk about something that's very important, a cross product. So how do we find a vector that is perpendicular to the two other ones? So given two vectors like, say A and B or V and U, how do we find something that's both perpendicular to both of them? And that's what's called the cross product itself. So the cross product is a vector that's perpendicular or orthogonal to both of them. Okay, so this is how we define our cross product to be. Okay, so again, where vector A, B are, actually, let me put it here. So vector A is considered A1, A2, and A3. And then vector B is B1, B2, and B3. So therefore, it's kind of a multiplication, but kind of funky. So this is the template of our cross product. Now, the good thing is very rarely will we actually doing the cross product of actual vectors like this written out. Most of the time, it'd be nice to do it in a matrix format for 3D-dimensional format, which makes it much easier to deal with because that's actually the determinant of a 3x3 matrix. But just in case you guys forgot completely about matrices and all that fun stuff, we do a quick little review here. So in matrix format, we use a lot. Here's a little review of the determinant of a matrix. So the determinant matrix is basically the value of the matrix or the value of that matrix itself. So for a 2x2 matrix, it is basically, again, kind of like, I always call it the crisscross, is you multiply these two minus the multiplication of those two. That's kind of the cross product. Okay. So, and then for a determinant of a 3x3 matrix, gets a little bit bigger. We have three matrices together. It is always the top rows always gets here, or if you want, some people can put it in the back as well. So it represents A1, A2, A3. So they're never in the matrix formats itself. And how it works is once you guys go into linear algebra, you'll see an nth space. It's always plus, minus, plus, minus, plus, minus. So in our case, the minus would be inside, always minus on the first one. And the other two are just additions. So their sign is always going to be whatever sign it is itself. Okay. And how you break this down is, here's A1. So A1 means you're going to cross this entire row out. So if you just put a finger over it, notice that's your matrix there. If you go to A2, I put my pencil over it, that's the matrix that's left over. And obviously last one, A3, there's your matrix there. So it breaks this down. So essentially you have to use the determinant of a 2x2 in a 3x3. Okay. So quick little example so you can see how it would work out before we get into the actual cross product of the determinants in matrix format. It's actually a lot easier than this, don't worry. But just for a little bit of practice. So we know from the top row it's going to be -2 times some matrix minus 1 times some matrix plus 4 times some matrix, right? Because that's our top row. And now if I cover the first row up, so this is all gone, I get 2, 0, 1, 7. Cover the middle up. 5, 0, 2, 7, and then finally the last one. And just please be careful, you have to put it in the order you see it from left to right. And now from here, we just do the 2x2 matrix. So multiply, subtract, multiply. Okay. So we have -2 on the outside. So this could be 2 times 7 is 14, minus 0, minus 1 times 5 times 7 is 35, minus 2 times 0 is 0, plus 4 times 5 times 1 is 5, minus 2 times 2 is 4. And then we just, keep going. So that's the 0, so it's going to be negative 28 minus 35 plus, this is 5 times 5 minus 4 is 1, so this is going to be 4. Right, and then we just add and subtract. So let's see what we get here. So it'll be negative 28 minus 35 plus 4. So about negative 59. There you go. And that's our cross product. Or determinant in this case. We haven't talked about cross product yet. Okay. Now, the good news is when it talks about matrices and vectors itself, our way of doing the cross product would be a little different. So if we have two vectors A and B with its respective components, the top row will always be I, J, and K, which is nice. So one less row to deal with. So hence the reason why I would be here, J there, and K there. So our cross product is defined to be this way in matrix format. And I don't know about you, but this is much easier to deal with than trying to memorize the actual cross product itself, normally. I usually just do the whole thing manually instead of trying to memorize that. It makes it a lot more sense dealing with it. So let's do just a couple examples. All right, so find the cross product if A is this and B is that. So we have A cross B is equal to I, J, K. All right, so -2, 9, and -7, -5, -3, and 10. So this is going to equal to 9, -7, -3, 10, I minus -2, -7, -5, 10, J, and then plus -2, 9, -5, -3. Okay. And then from there, we do the same thing, right? So now we create the determinant of 2 by 2. So 9 times 10 is 90. Minus -3 times -7 is -21. -20 minus 35. And then 6 minus a -45, so it gives you +45. And, now we just finish up by the subtraction. So 90 minus 21, so 90 minus 20 is 70, so this is 69. This becomes -55. Subtraction becomes positive. And then 45 plus 6 is 51. And there we go. So again, just for practice sake, we'll just do one more. Get you guys really comfortable with the cross product. Okay. So again, this becomes 0, -3, -2, 0, I. Okay. All right. So 0 -6, I. 0 negative, so this becomes positive, positive, so this is minus, sorry, -3, J. And then finally, do that. So here's our cross product. There we go. All right. So now we have an idea how to create the cross product, or how to do the actual value itself. Now, what's so important about this? Now, I said earlier that it's perpendicular, and that's the key. That's one of the biggest keys of the cross product is the vector A cross B is orthogonal to both A and B. Okay. And therefore, two non-zero vectors A and B are parallel if and only if the cross product is 0. That's another big thing as well. So those are two big consequences of the cross product as well. Okay. Now, just like everything else, okay, we define what this is, but what does it really look in three-dimensional space? So we have this going on there. All right, so we have the XY plane here. So now, if I have just two vectors, so let's suppose I have vector A going this way, and then vector B going this way. Now, given two random vectors, this cross product is actually orthogonal, meaning it's just going straight up. Now, just like the dot product where we have the multiplication of the angle between it, we also have an angle between the two vectors we're doing the cross product of, called theta. Well, remember, it's orthogonal, so these are automatically right angles there. Okay. So you can kind of think of it as, kind of a box shape, but this angle theta is, it can move however I want it, like a swing. Okay. So I can make it look like this, almost flat. And this is still perpendicular in both directions. Okay. So just like it for the dot product, our actual definition of the cross product, or the length of the cross product, will always give me this. It's the length of the individual vectors times the sine theta. So, right, key component is the dot product length. We have the cosine. The cross product length, we have the sine theta. So really, really big difference there when it comes to it. All right. Now, like I said, what does this mean to us? Like, what does it actually do? Okay. And this is actually pretty interesting part. So this is where the course gets pretty weird and pretty crazy. How, something very simple can actually make a big deal geometrically in, in everyday life. Okay. So what I mean by that is, again, given any two vectors, A and B, so let's suppose we have vector A and vector B. And how this works is, let's suppose I have this down here with this angle theta. So therefore, this length here would be the length of B sine theta. If just in case you forgot it from pre-calculus as well. So now if I do the lengths of each one, given this angle here, so doing everything exactly the same, I just give you guys the lengths. What this cross product is saying is, because it's orthogonal, it touches both of these vectors here, and it actually creates a parallelogram. And we talked about that last time when it came to the dot product. But this time, however, it actually gives us something called the area of the parallelogram. So since the length of any parallelogram is base times height, and this is actually equal to length of the cross product. That's the crazy part. Well, that's if theta is equal to pi over 2, right? Exactly portion. So that would give the exact rectangle. But now if theta could be anything we want it to be, this always gives us a parallelogram, which is also, pretty interesting. So again, in the special case, when theta is pi over 2, area is just this length times width, or just a rectangle itself. That's pretty cool part, is the length of the cross product actually gives you the area of a parallelogram. And so much so that we actually get a definition up here. So length of the cross product A and B is equal to the area of the parallelogram determined by A and B. So therefore, we can do some more stuff to it now. So now that we know what the cross product is, we can add more stuff to arsenal from what was last time when it came to orthogonal and perpendicular and parallel. So for example, question 1 here says, find the vector that is perpendicular to the plane and passes through the points P, Q, and R. All right, so to find a vector that's parallel, well, all that means is we have to find, to find a vector that's perpendicular. Well, the only thing we know how to define perpendicular is unit vectors and now cross products. But since we want it both to these 3 points, our cross product is going to be the case. But first we have to find our vectors. So we have to define 2 vectors. We're going to call it PQ and PR. So to find vector PQ is like we did last time. It is the end component, so Q minus the initial point, so P. So be -2 minus 1, it gives you -3. 5 minus 4 is 1. And 1 minus 6 is -5. And on the other side, we do the same thing. 1 minus 1 is 0. -1 minus 4 gives you -5. And then 1 minus 6 gives you -5. So now that we have our 2 vectors, we'll call this like, A and B, if you want to do for our definition. Now we can find the vector that's perpendicular to it, which is just the cross product. And now we just do the same thing we did last time, right? Just did the little simple little cross product. So this gives us 1, -5, -5, -5. Lots of fives everywhere. Yep. And therefore, this is going to equal to -5 minus 5 times 5 is 25. 15 minus 0. And positive 15 also minus 0. So what do we have? So negative 30 I minus 15 J plus 15 K. And there we go. Any questions so far? No. Yeah. All right. Okay. So now that we have a vertical, we know what perpendicular is orthogonal, right? So now I want to find exactly what that definition gives us. Find the area of the parallelogram spanned by the vectors A and B. So all that means is, again, find the cross product and then find the length, because that's what we're looking for. So I'll quickly set this up since we had some more examples of this already. What am I doing? So it gives us that first. So find our vector that's perpendicular. So we get 2 times -1 is -2, and that's going to be 0. So just ends up being that. Let's see here. So we get, I'll just do this 0 plus 2J, and we get 0 plus 2K. So our vector is -2I minus 2J plus 2K. Okay. So that's our cross product. And then we want to find the length, because the length would give us the parallelogram itself. So now we do the length of this. That's going to equal the square root of 4 plus 4 plus 4 is square root of 12. And there is our area of our parallelogram. So, like everything else, we have lots of different properties when it comes to the dot product. Or sorry, the cross product. And, some of these you actually be doing in your homework as well. Some of these are pretty straightforward. So like for our case, we're going to be doing the proof of number 5, and a couple of these are proved in your homework as well. So again, all this is just a couple properties, break this stuff down to see how the one goes to the other one itself. But we're going to begin doing the proof of 5 in class right now. So for number 5, we'll say, let's say vector A is the components A1, A2, A3. And then same thing for B and C. So we want to show that the dot product of the cross product equals, basically it's a cumulative property, right? It could be forwards or backwards. So we're going to start with this part here. So we know the cross product of B minus C, and that's going back to the actual definition, right? So I'm going to skip the matrix format and just go by its definition format, and that's going to give you this. So just using these two, it's going to give you B2 C3 minus B3 C3, or sorry, C1. That's the first component. Next component, B3 C1 minus B1 C3. And then the last component, B1 C2 minus B2 C1. And again, that's just using the definition. And now we're going to create the dot product of this. Now remember, the dot product, all it is just multiplying each component of A, which each component of the cross product. So basically, is each one of these is multiplied by its component there. So it gives us A1 times this plus A2 times the second component and then the third one. So therefore, multiplying all this out, or distributing if you want. And now, rearranging stuff. So in other words, if I would look at all the C1s, so I have C1 here and C1 there. And if I just put them together and factor it, so in other words, what I mean by that, I just do this. So I'll have A2 B3 minus A1 B3. Oh, yeah. Wait. Oh, this should be a C2. Thank you for that. So let me start over here. So it's actually this one and this one. Thank you for telling me that. Yeah, this one right here. All right, that looks better. Perfect. Okay. C1 plus. Now we go to C2s. So C2 is here and there. Good. So I only have two C2s now. Ooh. Scared me there. All these letters everywhere, you don't get confused. You see that? And then finally, this first part there is actually the cross product of A and B. Done. Now, there's a reason why I chose this one to do in class and not any other one, because there's some of them that are very, very simple, like number 1, very simple to do. 5 and 6 are the most difficult to deal with. But why 5? So, question is, why is this so important? Or what does it mean to us in the calculus portion? So, let's do this geometrically, and then we'll do the actual interpretation afterwards. So, basically what this is saying is, let's suppose I have 3 different vectors going on. So let's suppose we have this one being B, this one being A, and some random one C here. Okay. So we know B cross C means it's a line that's perpendicular to C and B. So it's not this one exactly, right? So even though it looks like, but let's suppose it's this one here. So this is B cross C, right? The cross product there. So if you notice now, if I put A at the end, right? This ends up being, if I find the length, it gives me a parallelogram. However, now, because I have 3 different vectors going on, I actually have this happening. I now have a box. And the cool part is now this length, this vector here is actually the height of this box. So this actually does give me a parallelogram itself, or a box parallelogram, if you want to call it. So that's the most interesting part, is a lot of stuff, we just don't make this out, this makes sense. Okay, what do we do this? It doesn't give us nothing. It actually does give some crazy stuff itself, and then how we can read things in 3 dimensions, just using simply, what we know so far. And so therefore, if this is a box or a parallelogram box itself, we could define what we just did as the matrix of that. Or in other words, the I, J's, and K's just go away and end up being matrix A itself, or sorry, a vector A itself, A1, A2, and A3, as we previously done it. So therefore, if you guys remember way back when you guys did matrices, and you guys will go over it again if you guys go into linear algebra, that the length of this vector that is created from all of this fun stuff is actually the volume of something called a parallel piped figure. And that's the most interesting part.